we hadn't seen a mob like this in my experience or Colloquium. It's been, a very inspiring couple of weeks. First of all, as a faculty member, there's nothing that makes us happier than seeing students succeed. And Joseph has clearly succeeded in spades. And the fact that we get to experience that firsthand and see what he's done is as gratifying as it gets. On top of the research and the success there, he was also the recipient of the acknowledgement of becoming a Goldwater Scholar, one of the first 2 Goldwater Scholars at UMass Boston. The other one is here as well, Sarah Dubois. And our technical difficulties have resolved. I give you Joseph Farah.
There's a lot of nerds in here. Thank you all so much for coming out today. My name is Joseph. I'll be speaking on behalf of the Event Horizon Telescope collaboration. I'll tell you about the first image of a black hole. So I'd like to start off with a quote, a very original thing to do in a presentation. I came up with this idea all by myself. But one of my favorite books is this book by Heinz Kegel called Perfect Symmetry, and in it he describes the astrophysics regarding, including black holes, which at the time no one was sure they existed. And he has this quote: "Wouldn't it be wonderful if a definite proof of the existence of a black hole could be found? Perhaps some is right around the corner, perhaps not. One would like the story of black holes to come to a conclusion with a bang, not a whimper." And on April 10th, 2019, we had that bang, and that was the first image of a supermassive black hole unveiled to the world by the Event Horizon Telescope collaboration. So M87 is an elliptical galaxy 55 million light years away. It is inconceivably far away and is appropriately inconceivably sized. It was discovered it was first imaged in 1913 in the optical wavelength, and even then, with the low-resolution telescopes, this very clear and prominent feature, this giant line kind of sparking out from the center, attracted a lot of interest. And this is M87 Jet. It's one of its primary features, considering that the rest of it is a dusty, boring blob. And this jet is extremely fascinating to astronomers, astrophysicists, physicists, cosmologists. Basically, anyone doing anything with high energy in science is interested in this thing. For one thing, it kicks off serious juice. At over 5 times 10 to the 49th joules. You can't wrap your mind around that. So let me give you some context. The entire Milky Way galaxy, in a single second, produces 10 trillion times less energy than this jet. The entire Milky Way galaxy that we reside in. And so we've imaged this jet in several different wavelengths. You know, we got great pictures from the Hubble, from Chandra, who's with us in this room.
Like the massive sun.
And radio telescopes, and radio arrays, so virtual telescopes. And the question is asked: what could possibly create a jet of this magnitude and power? And as pretty much in the last 50 years or so, whenever something extremely powerful needs to be crammed in an extremely small space, we turn to a black hole. And even though we're not sure if they exist. So Einstein's theory of general relativity, he published it in the early 1900s, and it treats space and time like an interwoven continuum, a fabric that can be warped by mass and energy. And this warping adjusts the trajectory of objects moving through it. And that includes everything from people like you and me to planets to things massless like light. And so his equations describe what we're familiar with, what Newton sort of showed us for gravity, which is 2 objects, if they have mass, will attract by a certain amount, but they also explain things that Newtonian mechanics couldn't, like the precession of the mercurial orbit. And they predicted things that no one ever thought was real. So for example, he predicted the apparent change of star positions during a solar eclipse as light is bent around the sun. And so Einstein's equations and Newton's equations agree on the same thing, that if you get a bigger mass, you have an increased gravitational potential field, you need to go faster to escape it. And so if you can get enough mass into a small enough area, you can solve Einstein's field equations for what John Archibald Wheeler later termed to be the black hole. This is Schwarzschild who solved for those field equations in the case of a non-rotating black hole. And Einstein didn't believe black holes could exist. He believed the math, but he figured there was no way that something so massive and so dense could ever possibly form in nature. But nonetheless, people continued developing the theory of black holes, and that's Kerr and Newman eventually developed it for the theory of charged black holes and rotating charged black holes. And so even though we didn't have any proof for the existence of these things, our understanding of them continued to grow. And so if we assume that there is a black hole at the center of M87, if we assume this assumption to be correct, we can estimate what properties it might have based on the jet and based on our observations of the galaxy. And so one of the things we can estimate is the shadow of the black hole. So as black holes have immense gravity, and as photons pass near it, their trajectories are altered. Some of them will get caught in this circular orbit where they're moving too fast to fall in, but not fast enough to escape. And this is called the photon orbit. Any photons inside of this get sucked in, and anything outside of it might have a chance at escaping towards our eye, towards our telescopes. And so what you see on the sky is you see this dark shadow representing the orbits where photons can no longer escape, surrounded by this ring of light. And that is, that's a very simple analogy to the image that we have all seen, of this puffy ring of light surrounding this dark depression. And we can estimate, if we take a picture of the shadow and we measure it, we can estimate things like the mass of the black hole, its angular momentum, its inclination relative to the observer. And we can use this to test general relativity. We can use this to learn more about how black holes might form, how black holes get to be so large. So understanding the shadow, seeing it, and measuring it is hugely important to astrophysics and physics in general. And so we can estimate, we take our understanding of how powerful the jet is and how big a black hole has to be created, and we look at stellar motions in the galaxy, and we can predict a mass for this black hole. We can predict the shadow size, because as the mass of the black hole increases, the shadow does as well. And so on the sky, we can predict that this black hole will have a size of about 30 to 40 microarcseconds. And a microarcsecond is really, really small. So if you take the whole sky, just a circle around the sky, and you divide it into 360 increments, that's 1 arc minute. An arcsecond is a 60th of that. And to your eye, an arcsecond is the same size as a headphone jack, 2.5 millimeter headphone jack, placed 8 football fields away from you. That's an arcsecond. A microarcsecond is a millionth of that. So imagine how small this thing is on the sky. It's the same size as a donut on the moon, or an atom held at arm's width. This thing is ridiculously, ridiculously small if our calculations are correct. And as I mentioned, the shadow and mass are intimately correlated, and so we can predict what the mass might be from watching stars move around the galaxy, watching gas move around the galaxy. And unfortunately, these two estimates give two very different values, both of them on the order of billions of solar masses, but there's a factor of 2 difference between them. And understanding which one is correct goes a long way to helping us accurately estimate the mass of black holes in other galaxies where we might not be able to see the shadow with such clarity. So we might be able to confirm which of these methods works better, or refute both of them, because these are just estimations of inferring the mass of the black hole in the center. So as I mentioned, the shadow is really, really, really small. And so what did it take to observe this? It took 2 things primarily. First, it took the hard work, unceasingly hard work of a lot of people over greater than 2 decades. So the collaboration, the Event Horizon Telescope collaboration, is over 200 people representing 60 institutions in 18 countries and almost every continent in the world. And every single one of these people has poured their heart and soul into this project, and without all this incredibly hard work, this ridiculous thing that has been accomplished would not have been achieved. And these people have worked, the last 20 years on pushing technology to the limits. Everything about this telescope is extreme. It's the biggest virtual array ever created. It's the size of the Earth. The telescopes are at the highest peaks on top of Mauna Kea and mountains in Mexico and Chile, and they're at the coldest locations in the world. In the South Pole telescope alone, temperatures get down to negative 70 degrees centigrade. And we record data at an incredibly fast rate. At the end of an observation campaign, we have 4.5 petabytes of data. and we record data incredibly quickly. We have the best atomic clocks in the world for taking timestamps on nanosecond scale. So everything about this project is ridiculous and extreme, and took an amazing amount of hard work to make it happen. And there's just one more thing that a project like this requires. So to do an amazing, amazing thing, you have to put in a lot of hard work. But to do an impossible thing, there's a certain amount of luck involved. And there is a lot of luck involved with the project. And I'd like to, there was a documentary published about the project by the Smithsonian, where they talked about at one of the telescopes during the 2017 observation, a component that needed to be cooled was not being cooled properly, and this is a very important component. And there wasn't an engineer with the expertise to fix this component, and so the scientists at the telescope had to come up with a solution. And the solution was to tape a door open and let air kind of flow in, and it led to this amazing quote in the documentary: "The piece of tape should hold the door open long enough for the observations to be completed. If not, the entire project could fail." And that may or may not be a very accurate representation of much of the project. But either way, there's a big luck component. And one of the coolest pieces of luck is the real specifics of the array. And so this is a very simple equation. This tells us the resolution that a telescope can achieve as a function of the wavelength it observes at and the diameter of its collecting area. And so, pushing radio astronomy and technology to its limit in 2017, we achieved an incredibly high frequency of 230 gigahertz, which represents a wavelength of about 1.3 millimeters. So we observed at this in 2017, and we had an array that was almost the diameter of the planet. And so the diameter of the planet is about 12,000 kilometers. And we need to achieve a resolution of at least, tens of micro arcseconds in order to distinguish the depression and the shadow from the flux surrounding it. And it turns out, when you take the best frequency we could achieve at all these telescopes at the time, and the length, the diameter of the entire Earth, you get exactly the resolution we need to see the two biggest black holes on the sky, which is an incredible coincidence. And it's incredibly fortunate that we're able to take advantage of this in order to take the first image of a black hole. So I keep mentioning this telescope as the size of the planet. And you might be wondering, how is it even possible? Where would you put a telescope the size of a planet? How much would it cost? And it turns out you don't need to build a telescope the size of the Earth to have an equivalent virtual telescope the size of the planet. So the image we might see on the sky looks something like this. This is a simulation by Avery Broderick from Perimeter Institute. And the EHT does not see this. The EHT sees something called the Fourier Transform of an image. So if you take a function, you can decompose it into the frequencies that make it up. So the same way, for those familiar with the Taylor series, you can compose a function of a series of, an infinite series of polynomials. You can compose an oscillating function of an infinite series of sinusoids. And then that function that results, which is this blue curve here, that's called the Fourier Transform. And it tells you information about the frequencies that make up the function. But the nice thing is you can do the Fourier Transform again to this, and what happens is you recover the original function, which is super useful. And so the way the EHT functions is like this. We have a source on the sky, and in this very simplistic model, we have two radio telescopes, and the signal is received by these two telescopes. And the projected baseline, which is the vector that connects these two telescopes, corresponds to a point in the Fourier plane. It corresponds to the point on this two-dimensional Fourier transform. And if you have infinite telescopes and you have infinite resolution, you might get a Fourier transform that looks like this. But the EHT doesn't have that. The EHT very sparsely samples this because we haven't covered our entire Earth with telescopes. We only have a partial understanding of the Fourier transform. And so the reason this is because, well, the reason we're actually able to get as much coverage as we do is because we take advantage of the Earth rotating. So a baseline, connecting two telescopes corresponds to a point in the Fourier plane, and we measure the flux at that point. And we measure the visibilities, combining the data from the two telescopes, and that gives us a data point, a single EHT data point. But as the Earth rotates throughout a night of observation, we get more and more data. The projected length of the baseline changes, and that gives us more information about the Fourier transform. More telescopes come into view, forming more and more baselines, and slowly we fill in the primary data product of the EHT, which is this beautiful double hump, this data product. And a quick shout out to the members of our calibration and error working group. So these are the three leaders of the group: Lindy Blackburn, Sarah Saoun, and Maciek Bugas. And it was their tireless efforts that brought us the these excellent data that we can use to produce these stunning images. And so you end up with a figure like this. So these are from the EHT papers, which show the telescopes as they probe the Fourier plane throughout the night, the baselines rather. And so this is a baseline from Alma in Chile to the SMT in Arizona. This is a baseline from Alma to Pico Valletta. And the more telescopes we have, the better we can fill this plane. And what you end up with is a sparse sampling of the source. So we sort of have this very loose idea of what the Fourier transform might look like, and it looks like this. And so now we want to image it. And this is a poorly constrained optimization problem, which I'll describe. So you have a series of points, right? And you want to fit a line to it. The more points you have, the easier it is to fit the line, but you don't need all of those points to fit a line if you kind of know the function you're looking for. And so you can take away more and more points and still get a line. But that fits pretty well and is an accurate reflection of the data. But the problem is you can sample so few points that this is not the only curve that fits the data well. And you might have a curve that passes through the points like this. And this fits the data just as well as that other fit, that perfect cubic polynomial. It might look something like this. It might be very smooth. It might be flat. There's an infinite number of functions that can fit this sparsely sampled data set. And we can combat this. We can make assumptions, some loose assumptions, based on other physics and other telescope information. And so this is an example. We can constrain where on the image, where on the graph the function is allowed to lie, and we can make an assumption a priori like that, and that constrains the number of functions that are possible. We can assume things about the form of the function, like how smooth they are. And so a very low smoothness might give you a ridiculous function that is probably not physically accurate, but if you keep increasing the smoothness, you might get something that looks better, and it might not be accurate. All three of these are equally valid. They're all equally likely to fit the data, but but we can enforce that the function that we fit be constrained by these regularizers, and this leads to one of the EHT's primary imaging methods, regularized maximum likelihood, which essentially goes beyond just fitting to the data and saying this is the image that best fits the data, but also says we know other things about the source. We know how it looks at longer wavelengths. We have zoomed out views of it. So we want to enforce, that the flux might lie within this giant region. We might want to enforce that, okay, there's not going to be a bunch of, random points on the image. It'll probably be something smooth. And we can find the best set of parameters that produces the best fit image. Now, as you saw before, you can just apply a Fourier transform to a Fourier transform and recover the original image. And that's also what we try to do. So there's a method called clean, which attempts to invert the Fourier transform and recover the original image, but it's difficult. We might have a source image that looks nice, but because we're not observing the entire Fourier plane, you get this thing called a dirty beam that is a result of all the missing information and all the noise you have. And when you try to invert that Fourier transform directly, you get a very corrupted and ugly image. So this procedure clean, this imaging algorithm, tries to determine source structure by saying, okay, we believe that this point, this very high, this very bright point is real. And then we subtract out the dirty beam from that. We try to self-calibrate to improve the Fourier transform and recover structure that might not be as bright as the flux that we're
And the
serving.
star is a convolution of a product.
Sorry?
The star is a convolution of a product.
The stuff?
The star, the star side.
Oh, that's a convolution.
Convolution, correct.
Okay. So both of these methods bring bias to the image, right? Regularized maximum likelihood. You can kind of get any image you want by messing around with the parameters. If you demand very, very strongly that this image look like a disk, you're going to get a disk. If you demand that it looks like a ring, you're going to get a ring. You can kind of tweak these parameters and really put unrealistic weights on them, and we want to avoid doing that. Furthermore, if you can put too strong of a prior on the image, you can make it, you rely on your assumptions too much, and that also biases your image. Clean relies a little too much on the user, so it's very much a user interactive thing, and it relies a lot on the expertise of the person who's using it, and that's fine. It's a very traditional method, and it has a lot of merit, but because there's so much user interface, it's difficult to script and check a bunch of different parameters and a bunch of different assumptions. And the bias that both of these methods have in common is that they're they're sensitive to the fact that very different images can have very similar Fourier transforms. So these are four very clearly different images, but they all very obviously have this double humped structure that is characteristic in EHT data. And we need to make sure that we can distinguish between these very different, these images that have incredibly different meanings, even if their Fourier transforms are very similar. So the way we avoid bias is by overall a two-step procedure: blind imaging and synthetic data tests. And so blind imaging works like this. Everyone brings their own assumptions when they come to when they come to make an image. If you worked on a telescope, you might trust the telescope's data more, or you might trust the telescope's data less. If you worked on the LMT during the 2017 observations. You bring your own assumptions about how much you trust the 3mm, 7mm priors, these observations along the wavelengths. You bring in assumptions about how you choose to image. You use regularized maximum likelihood, you use clean, you use some other other forward or inverse modeling based approach. And so the best way to figure out what features of your image are resistant to different methods is to have a bunch of people using different methods secretly image and then compare the images at the end. And so that's what we did. So we had 4 imaging teams working in secret to produce an image. They were given the data and given 70 days to produce an image. And then they all use different methods and then kind of a mix of RML and clean. And they all have different assumptions. They all have different expertise. They all have different backgrounds. And then we came together for the imaging workshop, which I ran along with Sarah Isaoun, Andrew Shale, Katie Bauman, Michael Johnson, who's here, and Kazunori Akiyama, the 2 imaging working group coordinators. And we all came together to try to produce an image silently, secretly, in a very barcode fashion. We had some discussions, had some informal presentations, and then at the end, we compared the images that we got. And so what you're seeing here is you're seeing the first images of M87 blindly imaged. So nobody talked to each other, nobody shared assumptions, nobody shared what they were doing, nobody mentioned anything about how they were approaching the image. And even though the images look different, they all have this feature in common that has stayed throughout the image until the one that is very famous now, and that's a 40 microarcsecond ring asymmetric towards the bottom. And that gives us a huge amount of confidence in that feature because with all of these different methods, we're able to recover the same feature from the data. And so this is the imaging working group at the imaging workshop. We're standing with a sort of loose consensus image, which is created by averaging those 4 images together. And I'd like to point out some faces. So that's Michael Johnson, who's here today, and Kazunori Akiyama, the 2 imaging working group coordinators. Katie Bauman and Andrew Shale, they're some of Katie led the synthetic data tests and the blind imaging in the group. Andrew was one of the primary developers on one of the regularized maximum likelihood libraries. And Daniel Palumbo and I, we're 2 of the youngest members in the collaboration. So he's a first-year graduate student, and I'm an undergraduate. And one of the reasons this collaboration has been so successful is because traditional barriers like race barriers, gender barriers, nationality barriers, international barriers, and age barriers are effectively removed because you have 200 people that only care about one thing, which is producing this image, and it makes for a very effective collaboration. And of course, the picture would be complete without the director of the project, Shepard Dolman, who's worked on this over half of his life. Okay, so the second way we gain confidence in our images is in synthetic data tests. So remember those really, really annoying sources that all look the same in the Fourier plane? Well, it turns out they're going to help us because we can generate fake data from them and test our imaging algorithms to make sure they're working properly and can distinguish them. And so we train our imaging algorithms on these fake sources, and then we try to see how well we can recover the original image. And so what you're seeing here is something very, very interesting. There's a legitimate concern that if you train on a ring, it makes sense that you see a ring. If you train on a disk, it makes sense that you see a disk. And so what we've done to combat that here is we've trained, so we have 4 sources, ring, crescent, disk, double, GRXD, and what we've done is we've trained on all of the sources except the one we're testing. So we've trained the ring by looking at disks and doubles, right? And what happens is that even though this algorithm has never seen a disk before, it's only seen rings and double sources and GRXDs, it's still able to recover the disk. And this gives us a lot of confidence in these imaging parameter surveys that look at hundreds of thousands of parameters and try to determine the ones that produce a best fit image. And so we take those best parameters, these fiducial parameters that work the best on all those different sources, and then we apply them to M87, and we take the best images from those slices of parameter space, and at the end, you have this image, which has been making the rounds. You may have heard of it. And so this is showing all 4 days of observation, and you get this beautiful puffy ring. It's very smooth. It's got the shadow that we can measure. Yes.
And what is the circle in the lower right?
That's a great question. So the circle represents the resolution of the EHT, of the Event Horizon Telescope. So the circle is kind of like a pixel in the image. We don't really trust anything smaller than this. And as a result, our image is effectively 60 by 60 pixels. So it's very low resolution, but it's enough to discern the shadow, right? It's just enough to see these giant black holes in the sky. So now that we have an image, we want to measure it, right? We want to estimate the mass and the spin and the inclination if we can. And I'm just going to talk about mass because spin and inclination are works in progress. So how do we do that? And this is an animation created by Don Pesci. He is a postdoc working at the Black Hole Initiative. And basically, we want to be able to, in a non-biased sense, and I'm sure you're probably getting the sense that the EHT is, a lot of what the EHT does is about removing bias from these methods. So we want to have a computer look at the image, robustly and without any bias that a human being might have, and determine what the size of this black hole shadow is. And so we design algorithms that take the images, this is called feature extraction, and they march around, and they look at radial profiles, how the peaks of where the brightest points of the image away from the center lie. And each of these bright points we call a radius, radius estimate. And at the end we have a histogram of them, and the mean of this histogram is our estimated radius, and the standard deviation is our error on it. But this isn't the only way that we can estimate the radius and estimate the properties. We can do this thing, we can use different geometric models to sort of say this is what a black hole might look like, even though it's not physical. A black hole might look like this, and we say how do these parameters correspond, the parameters of the model correspond to the real physical parameters of the black hole. So this is an example of a crescent model, which basically takes a disk of light and subtracts out a smaller disk from it. And there are a bunch of parameters here. There's the radius of the smaller disk that you're subtracting. There's where it's offset from the disk. There's the orientation on the sky. And so we can perform Monte Carlo simulations, and we can march around a parameter space consisting of all these parameters and determine what the best fit model might be, what those parameters are. And that is another way of estimating. Oh, sorry, yeah.
Well,
I can't see you.
Yeah, but I assume that other factors like the spin of the black hole and stuff orbiting around the black hole would create some sort of giant change in that. Like it's obviously not a ring. It obviously has bright passes, and that's because it's spinning and other stuff. So you have to don't they have to account for all that?
So that is a
Are they measuring the black hole radius or the radius of the accretion disk?
Sorry, what?
Are they measuring the black hole radius or the radius of the accretion disk?
We're measuring the radius of the shadow, which is about 2.5 times larger than the event horizon. And that's a really good question. What else affects the shape and size of the shadow? And actually, how spin affects the shadow is a project that I've been working on for quite a while. And I can tell you right off the top of my head that a black hole spinning at as fast as it possibly can, looking at it from an angle where you see the most deformation, doesn't change the mean radius by more than 4%. And that's well within the error margins of our radius measurements. So we can't really, right now, we can't trust from images alone what the spin of the black hole might be. And that's assuming you're looking at the black hole edge on. But we actually are potentially looking at the black hole down the barrel, in which case the percent error on how much the radius changes as a function of spin is basically 0. And so regarding the other part of your question, which was about how stuff flowing around the black hole affects the shadow, the nice thing about observing at such high frequency is that most of the gunk that's surrounding the black hole that would obscuring our view of the shadow is translucent at these frequencies. So we really, really only see the stuff that is just about to fall into this. Super accelerated so much it's putting out all the synchrotron radiation.
Oh, so we're not seeing the accretion disk, we're seeing this stuff falling into the field.
Yeah, we're seeing stuff falling right through the shadow.
Okay.
Orbiting right before it falls in, and this is part of the accretion disk. Okay, and so we don't just have to use geometric models. If we assume general relativity is correct, then we can use real simulations. So we can do the same procedure. We can take the simulations that have parameters, and we can explore their parameter spaces to find the best simulation that fits the image. So we can play with things like how fast the black hole is spinning, what its inclination is, the mass, its orientation on the sky. And these match more closely with the simulation parameters. But at the end of the day, these are three different ways of getting a radius, right? We can measure from the image, we can use geometric models that are very not physically motivated, or we can use like physically motivated black hole simulations. And if these three different approaches give us the same radius, then we can be more confident in that radius estimate, and as such we can be more confident in our mass measurement. And so all three of these radius measurements, even though they're pretty different, give almost exactly the same result. So they give a radius of about 39 diameter of about 39 microarcseconds, and that corresponds to an estimated mass of M87, which is about 6.5 billion solar masses. Which, if you notice what this plot is showing the mass estimate based on gas dynamics, which if you'll recall from the beginning of the presentation, and the mass estimate based on stellar orbits. And it's very obvious that our conclusion is that the stellar orbits are probably the more accurate mass measurements, which is huge, because now we can take this conclusion and apply it to other galaxies and to estimate the mass of other black holes. And 6.5 billion solar masses is kind of ridiculous. The sun alone is much larger than the Earth, and the Earth is much larger than anything we experience on a regular basis. But to give you some context, here's an animation created by Lindy Blackburn. He's a postdoc working at the Smithsonian, and he previously worked on the LIGO project, which measured the first gravitational waves. And now LIGO gets a lot of hype, and it looks at it looks at stellar masses, a stellar mass black hole. But M87, and this is a log plot, is just orders of magnitude, 6 or 7 orders of magnitude larger than anything LIGO can even see through watching black holes merge. And that's really what we're seeing on the sky. We're seeing this enormous object that's 6.5 billion solar masses. And we've managed to take a picture of it. It's so far away, it looks just absolutely tiny in the sky. We managed to take a picture of it anyway. And it's a really cool thing that we can appreciate. We've essentially just took the entire Earth and we've used it as our scale to measure this giant object 55 million light years away. And it really was a global collaboration. It's not just a global telescope. It is an international group of people working together, to take this first image, and it's something that could not be possible without, everyone, different countries, different institutions, and different, paths, different stages in their career working together to produce this image. And it really did take, a huge amount of effort to do so, and it's an incredible thing. And so what happens at the end of it, you get a picture that is above the fold in every newspaper in the world. It's a picture that is on the front page of every magazine, of every news site, science or otherwise. It's something that is it's something that's inherent to humanity. It's this thing that cannot be seen that we just decided to take a picture of anyway. And when was the last time you saw a mass measurement on the cover of the New York Times? It's a thing that's universally gets people excited, and universally. Look how excited Mars is. And from left to right, people in this picture are Daniel Palumbo, grad student, Dom Pesci, who made the feature extract animation, Carrie Hayward, an engineer, working on SMA, Maciek Wilgus, a postdoc, and the Calibration Error Work Group, Chef, the director, Michael Johnson, me, and Alex, who's in the back over there. Alex Rankin. So I'd like to leave you with this picture. This is Shepard Dolman, the director of the project, kind of staring in bliss at this thing that he's worked over half of his life to take a picture of, right? Since he was, for over 20 years, he's been working to take a picture of a black hole. And this is at the imaging workshop where we finally started realizing that, oh my God, everyone's getting a ring, this is really happening. There's actually a shadow, and everyone's images are very similar. So I'll leave you with that. Thank you so much for listening.
Tell us how big it is in arc seconds. How much? What's the actual length like at that distance?
That's a good question. Actually, do you know off the top of your head? Yes, actually. So there's a really nice. I don't know the number off the top of my head, but there's a really good XKCD that came out that shows sort of solar system. That shows the solar system inside of M87, right?
What was the question?
What's the size of M87, like the actual diameter? Do you know what it is, like raw number?
You said in arc seconds.
No.
Yeah.
He wants
Well,
it in like,
you told us its diameter in arc seconds, right? Like,
He wants to figure in furlongs.
yeah, like solar radius.
40 micro arc seconds.
In
and,
FU.
the first distance is about 10 to the 15 centimeters, which you can convert to your.
Which is really, really big.
that's how big the black hole radius itself is.
Yeah. And it just engulfs the solar system. You put
Holy shit.
the solar system here. This is the sun, and then over to Pluto is like you can barely see it. It's ridiculous.
You can,
Yeah.
you can at least feel.
It's kind of insane. Good question.
Maxine?
Yeah, just in 2 words, I mean, what would spin affect on the image? I mean, what would be you said it's hard to see, but what's the first measure?
So the spin, so as the black hole shadow looks like a circle when it's not spinning, when the black hole isn't spinning. And as the black hole, as you increase the angular momentum and the inclination, so you go from looking down the barrel to edge on, the black hole shadow deforms, flattens on one side, and then shifts over. Yeah. So it starts out as like a circle, and then it turns into the shape that looks very similar to the geometric shape called a lemmason. And so it has this like flat edge at maximum spin. And so this is a little hard to see when it's not that huge of a change. But the other way that we can tell, when a black hole spins up, the flux also redistributes itself. So you see more flux on this end and less evenly distributed around. And as you change the inclination, because of Doppler boosting, you end up seeing, because of Doppler boosting, more of the black hole is very dim compared to the brightest points. And so actually you can see Doppler boosting in this image because the black hole we think is slightly inclined. And so because there are photons moving towards us and photons moving away, they appear dimmer than the photons moving away appear dimmer than the ones moving toward us. It's
The direction of the jet gives you the
Yeah.
spin axis.
So we can predict we can sort of have a good estimate for the direction, for the inclination and the spin axis by the direction of the jet. But it's not necessary that the black hole be perfectly aligned with the jet. So that's a big issue.
Alexi?
So I think it's related to the previous question. What information you can get from 4 days of data, like April 4, 5, 6, and so on?
That's a great question. So
What was that question?
what information can you get from the 4 days of data? So that's a terrific question. And the first and most exciting thing is that it's a way of testing to make sure that the thing we're seeing is not just a fluke, right? It's not just an accident of the telescopes all malfunctioning at the same time, right? We get a very similar image for all 4 days, which boosts our confidence in any single one of them. And even though our resolution is kind of not terrific, there is a possibility that we could be watching, a hot spot moving across the base of M87. Like we've worked really, really hard to make sure that we're removing any effects of, the beam pattern on the image and low resolution UV cover. And so it is, we do see a distribution of brightness change from day to day. And this is actually pretty interesting. So M87 is really, really, really big. And so it evolves like very, very slowly. It took 4 days of data collection to see even the smallest bit of potential motion across the disk there. But Sagittarius A star, which is our next target, is much, much smaller. And it's so much smaller that we can see these kind of changes on the timescale of minutes during an observation. So this could bring the possibility of black hole movies, which would be really cool. That's a very good question.
So if we can see it evolve, then is the black hole recent? Can we tell whether the black hole recent disk is spinning clockwise or counterclockwise relative to us?
That is a good question. So we can.
What was that one?
Which way is it spinning?
Which way is it
What's
spinning?
the orientation of the rotation?
So we can
See
tell
it
we can tell the orientation of the rotation by looking at the Doppler boosting.
Yeah, but the Doppler boosting shows which side it's brighter on. It's brighter on the side that's going closer towards us. So wouldn't it be? So that spot's brighter. That doesn't mean it's tilted like this. It means it's tilted like this.
Right. That's correct.
Or maybe like this. We don't know.
That's true.
So,
One of the ways that we can determine the direction of motion is by watching flux move across the black hole disk, and so that would give us, if we, something like this gives us a reasonable idea of which direction, whether it's spinning counterclockwise or clockwise. And actually, paper 5, the 5th paper of the kind of EHT results, a lot of it was devoted to sort of looking at black hole spin, different simulations of black holes and how the direction of spin affects the flux. And so we can use simulations, we can use the Doppler boosting, we can use what could be potentially hotspot motion to make an estimate of what direction we
You
think the
mean
black
like,
hole is
so, you mean like it would, like I see like it looks like it's bright here and then it sort of gets dimmer
Yeah.
over here.
And that could potentially be a hotspot moving across. But we need better resolution to sort
But
of.
we don't know, we can't tell so far which direction it's spinning, we don't have enough information.
Was there a definitive conclusion on the direction?
Yeah, so it's a little counterintuitive. What we know is that the black hole's spin axis is pointed away from us, and so it's going clockwise on the sky. That's why it's bright at the bottom using the right-hand rule. That's the stuff that's coming towards you. What we don't know is whether or not it's prograde or retrograde. So it's actually possible that the black hole is spinning the opposite direction of the accretion disk, and it would still look like this. So,
You mean, so the accretion disk is spinning clockwise, but we don't know which way the black
so
hole
we
is.
know the black hole has to be spinning clockwise, but the accretion disk could be going clockwise or counterclockwise.
Okay. Okay.
Any other questions? Dr. Holland.
Yeah, so you showed us that different teams use different regularizers for other algorithms, right? And they didn't talk to each other, so they were independent.
Yeah.
However, great minds think alike.
That's a good point.
So were the regularizers alike or not? Since they got similar images.
So that's a great question. And so if you look at teams 1 and 2 use regularized maximum likelihoods, so they use regularized. But teams 3 and 4 did not use regularized maximum likelihood. They didn't use besides the prior assumptions for like 3 millimeter longer wavelengths. They don't have as many regularized knobs to turn as the RML methods. And so these are two they're completely opposite approaches. One of them attempts to sort of generate images and then take their Fourier transforms and compare them to data. The other one directly tries to invert the Fourier transform. And so these approaches are, you bring up a very good point. And when you look at images of two different regularized maximum likelihood libraries, they look more similar than they do to the clean method. But that tells us what information we can trust from the image. And what they all have in common is that 40 microarctic with the asymmetry tools is out. Yes.
But all of them knew what to expect. They all
No.
knew. They all did. I mean,
Nope.
They never seen simulations.
Yeah, so they've seen simulations, but that's part of the approach, right? Putting aside what you're hoping to see and just trying to make the best image possible. And everyone knew that. Everyone has seen simulations and know that it kind of looks like a ring. But generally, the Kerr metric is not the only theory of gravity. It could look like something different, and it could be like other sources that are not necessarily.
Sure, but everybody expected to see a ring and a dark
I don't
place.
think actually. So M87, we expected M87 to be very hard to image, and so we were not expecting at first to see a ring at all. We were expecting, some of us were expecting just an incongruous mass because our imaging algorithms would fail on it. So we have to, there's definitely a very strong incentive to be like very kind of upfront and honest about your assumptions and what biases you might have and what you're assuming about the image, because you could be assuming something that is very, very wrong. And Katie Bauman did her thesis on this kind of blind imaging procedure, and one of the things that was really interesting about it was these imaging competitions. So basically, you'd be given an image of something that you have no idea what it is, and it doesn't have to be a black hole. For one contest it was a snowman, for another person it was like a human being, and you're given how the image would look on the sky through the EHT, and then you have to use your imaging algorithm to recover it. And so you can't assume it looks like a black hole. You can't assume it looks like a ring because it could be a snowman or a person or a sailboat. And so you really have to. We got good at developing algorithms that are really good at putting aside previous assumptions and what we expect to see through these tests where we train ourselves to be better at ignoring this.
So it would be nice if you had then a final competition, not really competition, where you have a bunch of fake images that are nothing like that are coming from God knows where, and buried in it a real image, and none of the teams knows which image is the real one, which one is the fake.
That is an interesting approach. Most of the final imaging stages were spent on these things called parameter surveys. So instead of trying to sort of test to see whether or not people are doing it well, we tried to script everything, make it as computerized as possible, and then make sure the computers are doing well. So we may not have been able to check, if we have the real image buried in a series of fake ones, you know, is everyone getting the same thing for that real image? What we were able to check was basically every possible combination of parameters that could be possibly turned to make this image. And almost universally across the parameter space, you see a 40 microarcsecond ring asymmetric towards the south. The ring might have different widths. It might be, you know, slightly elongated in some images. There might be noise all over the place, but every single one of them has this ring. And so there's almost no combination of parameters that you can do, you know, within reason that can produce anything but a ring, which is extremely like encouraging because these algorithms are capable of reproducing snowmen and people and sailboats.
I think the snowman has nothing to do with the recent rating of EHT.
Yeah.
So to increase resolution, do you go to orbiting telescopes? Or?
That is a great question. So there are 2 ways to increase resolution, right? So in that formula we have resolution is equal to the wavelength divided by the diameter of our dish. So the 2 things we can do to increase resolution are we could make a better virtual dish by putting more telescopes within the plane so that we can, like on the Earth, so we have better and more accurate coverage of the Fourier Transform. Or we can go to space and we can have even, you know, the baselines extending from Earth to space would be enormous. And so that would give us very, very, very high, very good understanding, potentially, of the high frequency, the finer grain, you know, points of the image, and that is equivalent to a better resolution. The other thing we can do is go to higher frequencies. And so right now we're testing 345 gigahertz at our sites because that would give us a 50% increase in resolution. And so there's a lot of options that we can explore for getting better images. We're exploring all of them. Good question.
Why was M87 chosen, and when might we expect the next pictures?
That's a really good question. So the 2 biggest black holes that we can see with this telescope are Sagittarius A star at the center of our galaxy and M87. And they both have, you know, their own complications. Sagittarius A star, we're looking through the dust and gas of our own galaxy. It's called the interstellar medium, and that scatters the image significantly. And that makes it harder to image. Because also Sagittarius A star evolves much faster than M87, so we can't meaningfully average data like we do to get a better image for M87. And we actually didn't know any of this. Well, I mean, we knew about these problems, but we didn't know that M87 was going to be so much easier to image than Sagittarius A star. We just started out with M87, kind of trying to build up to Sagittarius A star at the imaging workshop, and then everyone was getting the same thing, and it was like super easy to image, and we pretty much devoted the rest of the workshop to imaging M87 and its calibrators. So it makes sense. I mean, we're not looking, you know, through all the dust and gas, like right through an arm of the Milky Way, and we're not, you know, M87 evolves much slower, so we can time average data, and it makes sense in hindsight, but we did not. We just tried to image both to the best of our abilities, and we did not know that M87 was going to be so much better to image than Sagittarius A star. And as for when the next image is, when we can expect the next images, I don't know. I mean, it took, you know, we've been sitting on this image since July 2018 and checking it in every possible, in every conceivable way to make sure it is the image, the best image that we can produce. But you know, who knows how long it'll take for Sagittarius A star. Hopefully, if we image M87 again at high resolution, it'll be faster. But we have no way to say. Good question. Yes.
When we do the Fourier transform and do all the cleaning stuff and stuff like that, how does it affect? Well, how does it affect stuff like small little blobs or that we want to see?
So that's a good question. So things like small blobs in the image, if they're smaller than the resolution of the telescope, then at the end they get blurred out. We don't really trust anything smaller than that resolution. Our sampling of the Fourier transform is so sparse that we only have a good understanding of the kind of broader features in the image. We can't really say anything definitively about things that are smaller, like, you know, blobs moving across the image.
So we're not looking at really high frequencies. We're just looking at the lower ones.
Well, 230 gigahertz is a very high frequency, but it's not high enough to give us really definitive information about things that are, you know.
Those images look, I mean, may look sort of similar, but not really. The team 1 and team 2 have these bright blobs on the left and bottom, but team 3 and team 4 just don't really have. Yeah, they're completely different. Like, how certain are we that there is a blob on one side, on that one side? Like,
Well, I mean, so these are not the final images, right?
obviously, but
these are. And this is really a conservative statement about what, from those images we were certain about. And the answer is pretty much nothing except the 40 microarcsecond ring asymmetric
Did
torsion
all
setup.
did all the pictures for April 5th agree that it looked like that?
Yeah, that's actually the really, really cool thing. So you take all these methods, and even though, so the regularized maximum likelihood methods are not constrained by the resolution of the telescope, so they can converge, they can crunch down to a higher resolution image than cleaning does. But you can convolve the image with the nominal beam, so you can say, okay, I don't trust anything smaller than this resolution, so we can multiply it by, we convolve it with a Gaussian of this size, and then it looks exactly like the clean images. And so, to the point where we trust the telescope's resolution, all the methods we use return the same image, which is very exciting. These are all great questions. Professor McCartney.
Did you use any machine learning approaches in your imaging this, or going ahead, is there a plan to do that? Because you have so much data, right?
He says about if there were machine learning approaches to the images. For the final images, I don't think there was any machine learning involved. There was no. There was training on data sets on huge surveys of parameter spaces, but I think there's machine learning. Like Katie Bauman did work with using machine learning to sort of construct images and try to find the best fit to data. It's one approach. I don't think it was one that was very strongly very strongly used. Unless the parameter surveys, was that like strongly machine learning based?
Well, machine learning is, people define it differently, but I would say this procedure of training your imaging algorithms and using the parameters based on those that perform best on a training set, I would consider this to be a machine learning approach, just a relatively crude one.
But it's still at its core, it's still a parameter-based exploration. It's still a bunch of parameters we're trying to, we might train an algorithm to sort of pick the best path, or make it, I'm walking through the parameter space, but it's still it's not a like, it's a combination approach.
But also maximum likelihood is nowadays it's a part of standard machine learning.
Yeah, that's true. Well, any technique of fitting data to taking an idealized thing and fitting it to like real data uses this inherent likelihood. Bayesian inference is huge. It's very effective.
Blake, did you have a question? Oh, I think kind of answered in that last go around, but it's not really machine learning unless it uses tens of thousands of GPUs and Google to join all your data, right? That's what machine learning means nowadays.
This is run on a supercomputing cluster. A lot of this.
So, if one did a calculation for what a black hole would look like inside the movie Interstellar, and you did this job right, is that what you expect to see
I mean, that's a good. They got as reasonably close as they could for our expression, but we would never expect to see something that highly resolved and that high resolution. Yeah, so a lot of our simulations and a lot of our models do essentially boil down to that, like a sort of asymmetric ring with some slash in front. But actually, the model that I was showing from Avery Broderick, there we go. So that's a perfectly valid model of Sagittarius star, and it doesn't. They don't always necessarily have to have that big slash. It's usually No, that's a good question. I don't think we have any information about. Yeah, we don't have any information about how Sagittarius stars are inclined. Hopefully, you should give us information about it. And fun fact about Interstellar, actually. How many people have seen Interstellar? Ah, good. But does anyone remember what the black hole is called?
Gargantua.
Gargantua. And do you remember why it was called Gargantua?
Big.
It was big. It was supposed to be, they're really trying to play it up. It's supposed to be the biggest black hole in the universe. It's like, oh no, we're accepted. This is the one time where fiction completely outclasses reality. Sorry, where reality completely just outstrips fiction. M87 is 70 times larger than Gargantua. It's just completely, just swallowed up whole. Dad.
I need a great question. I heard that the black hole does not spin, but it's sitting on a large turtle.
It's turtles all the way down. Any other questions?
Turtles always on the other side. If there are no other questions, I think we should thank Joseph.